All right. Hello, everyone. Welcome to class. So this is another session 11.9. And in section 11.9, our study is going to focus on representations. Okay, how to really represent functions as power series. Representations of functions as power series. Okay, so this is really a nice application of calculus. It's one of the beauty of Calc 2. Ability to learn this method where you can write functions as power series. Okay, so the motivation or the question we're trying to answer is that how do we write functions as a power series? Okay, so if I give you a function of x, okay, can you write that function as a power series? Okay, so we would be able to answer that question at the end of the day. Okay, so can we just start from, now let's start from building. Let's recall the geometric series. Now, remember the sum is given by a divided by 1 minus r, all right? Now, this guy is the same thing as a plus, okay? Because this is just the sum, right? This is a geometric series as n goes from 1 to infinity. Okay, so, and of course, remember when we learned this, we said this guy has two representations. This is another one. This is ar to the power of n. Now, when does this guy converge? Okay, remember when this guy is less than 1. And when it does converge, we can find the sum. Okay, so this guy, a divided by 1 minus r, is the sum of this geometric series, right? So, and of course, you can only find the sum when you're sure that it does converge. Okay, so now what if in the case where our a is 1 and our r equals x? Okay, so what if our first term is 1 and our r is just x? Now, what do? Just plug in a and r in this equation you have on top. Okay, so you have 1 divided by 1 minus x equals 1 plus x squared plus x cubed, and this continues on and on. This is the same thing as this guy, right? This is just, I'm just replacing my first term with 1, okay? And of course, for this guy less than 1. So it's pretty much like the same condition, but you're just making those substitution. Now, finally, what do we see, guys? So hence, 1 divided by 1 minus x is the same thing as this guy, okay? So that means this sum, this is a geometric series. The sum of this geometric series is just 1 divided by 1 minus x. Now, this is very important, guys. So let me just box it. Okay, so this is very important to us. We need it going forward. All right. Now, as a basic example of how to apply this example, express 1 divided by 1 minus x to the fifth as a power series. All right, so solution. Now, keep in mind that now that guy I have in the box is, recall that 1 divided by 1 minus x equals the sum as n goes from 0 to infinity, x to the power of 5, right? This happens for absolute value of x less than 1. Now take a look, guys. This example is 1 minus x to the fifth, okay? So that means that I can also do some kind of substitution It's 1 minus x to the fifth. So wherever I have x, just replace x. Oh no, this should just be x alone, guys. This is x to the n, sorry. So that means that wherever I have x, replace x by x to the fifth. Okay, so this is going to be a sum as n goes from 0 to infinity. This is x to the fifth, then you have n. Okay, now can you see the importance of this guy I have in the box? We build based on this guy. All right, so this example was x to the fifth, and this is just x. So that means you want to replace x by x to the fifth, and that's exactly what we did right here. Okay, so we move on. So this guy is the same thing as, of course, you remember indices, this is x to the 5n. Okay, so this guy will converge. When will this guy converge? It will converge for this guy less than 1. Now, remember that, guys, the common ratio. In this case now, the common ratio is not just x, it's x to the fifth. Now, if x to the fifth is less than 1, what does it mean? It really means that my absolute value of x is less than 1. Just take the fifth root of both sides. The fifth root of 1 still gives me 1. Now, so what can I see? Okay, what can I really see? Okay, so now what happens? Okay, so let me not skip step. So this means that 1 divided by 1 minus x to the fifth is just this guy, n from 0 to infinity, x to the power of 5n for this guy less than 1. Okay, so now what if this guy is x divided by 1 minus, okay, so let me just write further illustration. What if we have x over 1 minus x to the fifth? Okay, so what difference will this make? Okay, the difference is in the fact that if you look at the top here, this is x, this is 1. So that means I'm going to have x times 1 over 1 minus x to the fifth. X times, what is 1 divided by 1 minus x to the fifth? And this is just exactly this guy on top, okay? So this is n from 0 to infinity, x to the 5n. Now, of course, this x can multiply this guy. So I'm going to have n from 0 to infinity. This is going to be x to the 5n plus 1 by loss of indices. So finally, x divided by 1 minus x to the fifth is equal to this sum. So you can now see that you can definitely really write a function as a power series. Okay, now let's look at another example. In this other example, we want to do something that is similar, but a little bit, we just have a little tweak, okay? So express 1 divided by 1 plus x to the fourth as a power series. And find the interval of convergence. Interesting. Remember from 11.8, we discussed the concept of interval of convergence, okay? Okay, so solution. Now, where do we always start from? Okay, we always start from this guy that I have in the box. Okay, this is where you're building from. Okay, this is 1 divided by 1 minus x. But in this example, this is plus. I mean, that means I really have to do something. Okay, so let me write it again. Recall that 1 over 1 minus x is just the sum for this guy less than 1. Right? Now this guy is a plus. This is 1 divided by 1 minus x to the fourth. Do you get that trick? Now because plus is just negative times negative, minus times minus, right? So because I need it to look like this guy. I need it to look like this guy. Okay. So, and this guy has a negative in the middle. So I need to find a way to introduce a negative sign. Okay, so equal to, now just the same trick. Wherever you have x, replace x by negative x to the fourth. N goes from 0 to infinity, negative x to the fourth. Then you have an n on top. All right, so this is equal to, now watch this. If you have a negative 5, negative 5 is the same thing as negative 1 times 5, right? All right, so and that's the same principle we're going to apply here. This guy, I can pull out the negative guy, so I have a negative 1. But keep in mind that this guy, there's an n right here. So you do have n times x to the 4n. Interesting. Okay, so in this case now, what is it going to converge for? It's going to converge for, in this case, I'm going to go back here because this is like my r, okay? So that's a negative. But remember, when you take the absolute value of a negative number gives you positive, so that means this guy is less than 1. If this guy is less than 1, what does it mean? It means that x, absolute value of x is less than 1. Now, how did I get that? Just take the fourth root of both sides. If you take the fourth root of both sides, you have that guy less than 1. Make sense? Okay, so now, but we're not done. The question further goes ahead to say that we should actually find the interval of convergence. Okay, so, and in this case right now, to put things really in perspective, okay, so as we had learned before, we always need to check our endpoints. Okay, so we need to check our endpoint because that actually determines a lot for us. Okay, now in this example, and this is a way to think about this. This is an interval, so we can decide to do, this guy is interpreted as negative 1 less than x less than 1. So remember how we do the test. You test the left endpoint and you test the right endpoint. Now, if you do it for this problem, in both endpoints, it's going to diverge. Okay, it's going to be divergent in both endpoints. Now, what do I mean by that? When x is negative 1, what happens? You plug in negative 1 here. So you have a n from 0 to infinity, negative 1 to the power of n times negative 1 to the power of 4n. Okay, so apparently this guy is going to give me a positive number, right? Because this power is even. So, and that means at the end of the day, I have something that looks like this. And this guy is divergent. Okay, so, and that's the reason why, if you do that for the other side too, the same thing would happen. Okay. Now, why? Because infinitely for this guy now, it's the behavior is not stable. Okay, remember that the behavior of this guy is what I mean. This guy is either +1 or -1. So that means you're doing a lot of +1, -1, +1, -1 for like the most part of the thing. Okay, so and the other guy too, on the other end too, you are doing it for like the most part of the thing too. Okay. So when x is 1, what happens in that case? This guy is going to be, you have a -1 you have a negative 1 to the power of n times you have a 1 to the power of 4n. In fact, if you don't want to go this way, you can even decide to do, in this case, I could have just done indices if I wanted, okay? So if I combine these two guys, I could have also got to negative 1 to the power of 5n. Okay, that power is still odd. Power of n. Okay, so let me give you guys 1 second to think about this guy. Take a look at it and let's see what you think about it. I'm going to give you guys a minute. Okay, so let me. Okay. All right, now this same thing, this same interval we showed, I need to also let you know that we can do that with the ratio test. Okay, you can definitely do that also with ratio test, and then we see what happens with that. Right, you can do that with ratio test and then try to understand the same interval. Okay, so diverges. All right, so at the end of the day, we just know that the interval I is given by this guy, or you can decide to write it this way. Okay, now this is happening because this case is different. Okay, it's a very basic case. I could have omitted this part, okay, because I just know from this example, looking at the form of this series. Okay, so let's move to another example. We start from the basic thing, then we step it a little higher here and there to see what is really going on. Okay, example 3. In this case, I want to express 1 divided by 3 plus 2x as a power series and find its radius and interval of convergence. Interval. Okay, so there's really a couple of things to achieve with this guy. There's a couple of things to do. First, show as a power series. Secondly, find the radius. Thirdly, the interval of convergence. All right, solution. Where do we start from? I always remind you about the basic standard that we need to build from. Recall that 1 over 1 minus x is this guy for absolute value of x less than 1. So I got to build from there. Now I have 1 divided by 1. This is 3 plus 2x. Now what did you notice, guys? The first entry here is a 1. So I need to find a way to make this guy 1. And right here I have a negative. So I need to find a way to make this guy negative. This is a 2. Okay. I need to find my way around some of those things. Okay, so let's start. At least, most importantly, you can retain 1 on this first entry. Okay, even if you cannot retain this guy to only be x, you can find a way to retain this guy to be 1. Now how do we do that? Okay, 1 divided by, If I want to make this guy 1, what do? I need to divide, right? Or factor out 3. If you factor 3, you do have a 1. You need a minus in the middle, so this becomes a negative minus 2x over 3, right? And this is equal to, now, let me scroll down a little bit. Now, you now have 1 minus something, right? So this is like 1 over 3 times 1 over 1 minus 2x over 3. Now, just like before, we replace x here by negative 2x over 3. So that means I have a 1/3. I have the sum as n goes from 0 to infinity. This guy is really going to be a negative 2x over 3 to the power of n. Okay, makes sense. So at least the first stage, the power series is given by this guy. So now I have to do ratio test. Okay, so that's a way to think about it. You can just go ahead and do ratio test. That's a way. Or if you want, you can do, you pick this guy in the middle. It has, for this guy to be convergent, that guy has to be less than 1. Okay, but let's do ratio test in this case. Okay, now to find radius and interval of convergence. Right? Now, an is negative 2x over 3 to the power of n, right? What is a sub n plus 1? This is negative 2x over 3. Wherever you have n, replace it by n plus 1. Now, with respect to ratio test, you remember my interest is this guy, plus 1 divided by an. So I need to find this limit. This is a sub n plus 1, so this becomes a negative 2. Of course, keep in mind, guys, I can simplify this guy to be negative 2 over 3, pull out the constant apart, and then you do have a x to the power of n times x. So do the same thing, just plug it right here, plus 1 times x to the power of n times n. So that's a sub n plus 1, dividing this guy by negative 2 over 3, and then x to the power of n. Let's see, can anything cancel? Okay. If I want, guys, I can even split this guy further. Okay, so this guy is negative 2 over 3n plus 1, right? So this is the same thing as, this is not difficult, guys. This is just indices, right? And why am I splitting it out? So that I can really see how things cancels out. So we're really left with limit as n goes large of 2/3 x. I mean, this doesn't have any n. So that means that my limit actually is going to be 2 over 3, an absolute value of x. Now, remember that by ratio test, when do we have convergence? Remember that your L has to be less than 1, right? So that means I'm going to do 2/3 x less than 1. Okay, so where do I go from here? This is 2. Multiply both sides by 3. 3 is a positive number. The inequality is not distorted. I need x up by itself. This means that this guy is less than 3/2. Right? Okay, so going forward from there, this is absolute value of x. I can rewrite this guy. Remember, we learned this from 11.8 as 3 over 2 less than x less than 3 over 2. Now, remember, for radius of convergence, you have negative r less than x less than r. So guys, what is the radius of convergence? Radius of convergence r is just 3/2. Okay, now can this guy be the interval? We don't know. You have to test the endpoint. Okay, so check endpoints. So when x is negative 3/2, you go back to your power series, which is this guy. Okay, you have to plug it in. Let me see. Now, when you plug it in, when x is when x is equal to negative 3/2, what do we have? Okay, when x is equal to negative 3/2, we should have a 1/3, and from 0 to infinity, you have a negative 2/3 times negative 3/2 to the power of what? N. Okay, so let's back up a little bit and make sure that everything is good. Okay, this is negative 2. X is negative 3/2. Yes. Okay, so we're good. This guy takes off this guy, this guy takes off this guy. So that means I do have a 1/3. Okay, this is 1 to the power of n. Now, what can we really see from here? We can see clearly that in this case now, I need to let you guys know that this constant up front at this point does not really matter. Okay, that constant does not really matter because we are not finding the sum. We are only trying to determine if it does converge or diverge. Okay, so it is okay to omit this part if you want. So, but I just retained it so that you guys can see what's going on. So, but what happens to this kind of series? Does it converge or diverge? It does what? It diverges. All right. When x is 3/2, in fact, um, this guy, if you have one, this is just one to, if you raise one to a number, it gives you 1, right? And in our case now, n is not negative. So if you don't want to think about it like this, you can still think about it as this guy. Something like this. Okay, so you can think about it this way. Let me just put, or this guy, which still diverges. So when x is 3/2, just plug in 3/2. If you do that, you're really going to have, this is negative 2x/3, and right? So we still have a 1/3 here, right? So we can maintain the 1/3. This guy becomes 1/3, from 0 to infinity, negative 2/3 times 3/2 to the power of n. So this guys cancels out. So, well, however, I'm left with n from 0 to infinity, negative 1 to the power of n. And this guy is the same thing as n from 0 to infinity, negative 1 to the power of n divided by 3. This guy is actually divergent. Okay. So what's my conclusion? My interval of convergence is negative 3/2, 3/2. If you don't want to write it in this form, you can still write it like this guy. They are pretty much the same. Okay, are we good? Now let's see another example. Find the power series representation centered at 0, okay, for f of x equals 2x over 3 plus 4x. Okay, so solution. Okay, again, in this case, what do we do? Remember what we really start from. We start building from here, right? I need this guy to be 1, and I need this guy to be a negative number at least, okay? So this is going to be, if you want this guy to be a 1, oh, there's an x here. Factor out x, 1 minus 4 over 3. Right? Now, let's see. Okay, so this guy is the same thing as 2x over 3, all divided by 1 minus 4x over 3. Now, if your algebra is very scratchy, okay, it's will be dangerous for this part because you really have to go back to the basics, okay, the basic algebra and fix things, because you see that's what we're really doing right now. Okay, so this guy is going to be the same thing as now. Compare, right? We need to compare. That means wherever I have x, replace x by negative 4x over 3. Okay, keep that in mind. Of course, this guy is the same thing as 2x over 3 times 1 minus 4x over 3, right? So this is 2x over 3 times, maybe sum n from 0 to infinity. Now remember, you're replacing x by negative 4x over 3 to the power of n. But we're not done yet. You cannot stop this way. This is x. You have to take it in. Okay. If you take that guy in, you have n from 0 to infinity, 2x over 3 times negative 4x over 3 to the power of n. Okay. Now, what do? We still do some kind of simplification. Okay. You got to tidy things up. Okay. So don't leave it untidy. So sum as n goes from 0 to infinity is 2x over 3. Now, if you look at this guy is the same thing. I can split this guy into 2 or even more than 2 parts if I want. This is a negative 1 part, right? Times, you have a 4 and times 3 to the power of, no, it should be x. Right? So just bring that guy in. X to the power of n divided by 3 to the power of n. Now, why is it important to split this guy out? Because I have to combine the x's, okay? So this is x, this is x. I cannot stop here. I have to combine them to a single thing. So to combine the x, you really need to spread them out, then you merge them, okay? So this is n from 0 to infinity. Now take a look. This is x, right? This is x. You see you can combine them. So this is 2 over 3, which is a constant, times you have a negative 1 to the power of n, 4 to the power of n over 3 to the power of n times x to the power of n plus 1. Now I'm taking it one step at a time so that It can all make sense. So I can write this guy even, bring this alternating term up front. I do have a 2 here, 2 times 4 to the power of n divided by, now look at this guy. This is 3, this is 3. I can combine them. So this is 3 to the power of n plus 1 multiplied by x n plus 1. And that's my answer, guys. So 2x over 3 plus 4x is the same thing as negative 1 to the power of n, 2 times 4 to the power of n, n plus 1 times x n plus 1. So you see, this guy is just all about simplifying, trying to split things out, trying to merge things where possible, and making sure they look nice in the end. All right. Let's move on. Now, we want to move on to something a little bit technical, but I want you guys to follow. It's going to be easy to work with, if you follow me closely. So differentiation and integration of power series. Now, let me define, okay? Now, the kind of integration we want to talk about here are term by term, okay? Term by term differentiation is the process and integration. Term by term differentiation and integration is the process of differentiating or integrating each individual term, just from the word term by term, okay, in the series. Now, we have a theorem. We are really going to talk about this theorem right now. And then we look at examples, okay? We'll look at examples. Theorem. If the power series, this is a power series, if you remember, power series centered at A. This is the center. Has radius of convergence r greater than 0. Then the function defined by f of x c0 plus c1x minus a. Guys, remember that we said when we started 11.8 last week that you can write a function as a power series, and we showed that today. And we're seeing it again right now. Okay, it's differentiable. Of course, if it's differentiable, it is continuous. And therefore continuous on the interval. So don't worry, I mean, it looks a lot theoretical right now because we're talking about theorem. When we start applying it, you see the beauty of what it's talking about. Firstly, remember it's term by term differentiation, right? So I begin to differentiate. Now, take a look at this f of x. Let me call this guy, let me use my red pen. Call this one, let me just say E, EQ, okay? Let me use EQ to represent equation. Now, if you look at EQ, differentiate EQ, C0 is a constant. Differentiate the constant, it gives you 0. But if you differentiate C1, this guy, you would even have a C1. If you keep differentiating each of those quantity, you begin to have this order of things. If I write this guy as a power series, it's going to be n from 1 to infinity, ncn x minus a n minus 1. Okay, so this ncn is not combination, it's not combinatorics. Okay, so don't think it is combination and permutation. No, that's not what we're studying. So we go back to the EQ again. I can integrate that EQ. Integral of that guy is c plus c0 x minus, the c is just a constant of integration, c1 x minus a squared over 2 plus c2 x minus a cubed over 3 factorial, of course. No, not factorial. This is just 3. This goes on and on. That means I can definitely write them also as a power series. Cn x minus a n plus 1. Let me shift this guy. Yes, okay. So all divided by n plus 1 plus c. That c is just a constant of integration. Okay, so remember what we differentiated and integrated EQ. Now, note, perhaps I use a red pen for that. The radii of convergence of the power series in the first two guys on top, okay, in 1 and 2 above, are both R. So the radius of convergence of the guy you see over there, it's R, both for the differentiation case and the integration case. Okay, so now we don't like the way this number 1 and 2 looks like. Can we actually rewrite it in a more mature mathematical way? Yes, we can. Okay, and I'm going to show you that. Then we apply them. Okay, it gets interesting at the level of application. We can rewrite equation 1 and 2. Now let's call it 3 to give 3. Okay, don't worry. Let me call this guy 3. As for the differentiation part, you differentiate the power series. What happens when you differentiate the power series? This is going to be, now this operator, derivative is an operator, can directly apply to what you have inside. Okay. Now, what about the integration guy? This is a sigma notation. So it's pretty much the same, right? That means this integrals can actually apply inside. So you have a sigma integral, this guy. Okay, now we need these ideas. Okay, we really need them. Now let's get to the interesting things. Example. Express 1 over 1 minus x squared as a power series. What is the radius of convergence? Okay, so in this case, we actually see clearly that over here we have a 1 divided by 1 minus x, then you have all squared, right? So solution. Now, what do we need? Right here, we need the fact that, so recall that this derivative, 1 divided by this guy is the same thing as 1 over 1 minus x all squared. All right. So let me box this guy so that you guys can be familiar with this as well. Now, what is the difference between what we're doing right now and what we did before? Now, what we did before, we had that 1 divided by 1 minus x being equal to, now remember, we're still working with power series, right? So, but now, this example, things are slightly different because we have 1 divided by 1 minus x all squared on the bottom. Okay, so this really changes things. You see, this guy is just 1 minus x, but this guy is 1 minus x all squared. So it does change things, all right? So you got to pay attention to this guy in the box. Okay. And keep in mind that this guy is generated from this guy. Okay, so this guy will produce this guy. How? When you differentiate this guy, you will get this guy. You can try it, okay? Okay, so let's move on. So, and 1 over 1 minus x is this guy. Okay, so what happens? 1 over 1 minus x all squared, remember, is when you differentiate this guy, right? d dx. Now let me use the red pen. This guy has a representation. I'm going to write the representation here. So pretty much we are going from known to the unknown. Now, but let's go back to this number 3. Number 3 says that this, your d dx, can apply really to what is on the inside. The d dx is outside, I can apply it inside, okay? So that means I can rewrite this guy as d dx of differentiate what you have on the inside. And if you do that, you have a n from 0 to infinity. This is going to be nxn minus 1. So in conclusion, guys, 1 minus x all squared is going to be equal to nxn minus 1. Okay. Now, but we're not done yet, right? Because the question is asking us about the radius of convergence. Now, if you take notes, we had a note right here. We say the radii of convergence of those power series are the same. Now, this equivalently, the radius of convergence of this guy, this part, and this guy will be the same. So 1 over 1 minus x squared has the same radius of convergence as 1 over 1 minus x. So my radius of convergence is 1. Why? Because the radius of convergence here is 1. Okay. So So, I mean, this video is, you can definitely, I know this part, just as I mentioned, as we keep going deep down into the class, we get to more technical details, okay? And you have to really be careful about them. So you can always see this video over and over again to get a hang of it, all right? So now let's look at, we're going to even step it up a little bit further. Express f of x equals x squared divided by minus 2x all squared as a power series. What is the radius of convergence? Solution. What is my f of x? I'm given this guy to be x squared divided by 1 minus 2x all squared. Now, when you have a variable on the top, you can even just split it, right? So that you can have 1 or a number on the top. Now, why is that important? So that we can use what we know. Okay, so we got to go from known to the unknown. Okay. Now, what do we do from here? Now, let me pick this guy, okay? 1 over 1 minus 2x all squared. Now, what can I differentiate to give me this guy? Now, let's go back to the first example. We went on with, now this is what we really needed was 1 divided by 1 minus x all squared. But we went on from, we differentiated something to give us that thing, right? So we do the same thing here. I need to, this guy, what can I differentiate to give me this guy? And this is 2 divided by 1 minus 2x prime. Okay, so if you differentiate this guy using quotient rule, you will get this guy back. And but I can pull out 2 definitely. All right, so this is what we're going to be left with. Now I can, again, let me use red now. Can you see what we're working with now? Can you see how we just do the twist and the turns? I'll refer you back to the first example I have on top here. Okay. So let's go back to this guy. Now, you see this quantity, this guy. We need it. Pick this guy I have on the inside, this guy. One over, oh no. Now, in terms of this here now, you want to replace what's your x by 2x, right? So I'll have a series 2x to the power n factorial. If you're not comfortable with my use of factorial, so let me just use ddx since that's what we've been using, okay? They are the same though. Let me just use ddx so that I don't get anybody confused. Okay, so I don't want to get anybody confused, so let me just use ddx. Now you can see that right now the ddx can go in. Okay, so I'm going to have a 0 to infinity ddx of 2x to the power n. All right. So this guy, if you differentiate this guy, you will expect to get okay, so this guy, when you differentiate this guy will start from 1. This is going to be a 2 n x n minus 1. Just do a derivative. Now keep in mind that this guy itself, okay, so I'm trying to split things down so that everybody can understand. Okay, look at this for a second, guys. Okay, I think we can move on. All right, so what do we see? So we can see clearly now. Remember that I didn't take these two along, right? There's a 2 up front here. So I can put things back in perspective. All right. So what is my f of x? Remember, f of x was x squared times, right? You had this guy, but what is this guy? This guy is 2 times something, right? So you do have a 2 here. Infinity, this is 2 to the power of n. Now you have to be careful. These are technical details, right? You have to take it one step at a time and make sure that you don't miss out on anything. Keep in mind that we don't want this x and these 2 to be outside. We need everything to be compact. All right, so this is 2 to the power of n plus 1. I do have a x, n, I mean, this is x2 plus n minus 1. Let us see. 1 to infinity, this is 2 to the power of n plus 1. This is, okay, right? This is times n times this guy's going to be x n plus 1. Okay, now there's something we often call, you can stop here, right? This answer is correct. Okay, this answer is correct, but let me tell you guys about something we call shifting index. Now, what does this mean? If I want this guy to start from 0, I need this guy to start from a 0, okay? If I need it to start from 0, think about n equals 1. I don't want this guy. Now I want n equals 0. So what would I do? Now, take a look at this guy, n equals 1. Just subtract 1 from here. If you subtract 1 from both sides, you will get n equals 0. N minus 1 equals 1 minus 1. N minus 1 equals 0. Think about that. So that means in this guy, this red guy, this guy I'm dotting out, whenever you have n, okay, so I don't want to lose anybody. Okay, so wherever you have n, you want to plug in n minus 1. All right. And then we can always check if what we did is right or not. Okay, so let's see. So remember, I want to plug in n minus 1, right? So that means f of x is going to be n goes from 0 to n minus 1 plus 1, n minus 1. Then this is x n minus 1 plus 1. So at the end of the day, I do have an n from 0 to infinity. This is 2 to the power of n minus 1. And then I have x to the power of n. Now, let us see. Now, the only part that really needs a last quick fix is the fact that over here, even if I plug in n equals 1, if I plug in n equals 1, yeah, I will have a 2 squared plus 1. So everything should be positive, right? So that means this guy has to be a plus 1. Okay, however, you can just stop here at the level of the, what's it called? At the level of the power series, okay? but let's see. Okay, so but however, most accurately, if you stop here, the job is not in the final bus stop yet, right? So to have it in the final bus stop of to the final point, you have to return this index back to 0. Okay, and make sure that things really align as they should be. Okay. So now, when will the series converge? Remember, the series should converge when this guy. Oh, let me start some words. Okay, so we just need the x to be up by itself, and then we can divide through by x, and then we get that. All right. So now that's with respect to differentiation, right? So what about integration? Let's consider examples that relates with respect to integration. Example 1. Now, okay, let me start from this guy. Find a power series representation and radius of convergence for f of x equals the inverse tan of x. Solution. Okay, so keep in mind, where do we start from? This is this is an inverse tan, right? I start this way. Differentiate my tan inverse of x and plus x squared. But remember that I think in one of the previous did we do that one? Okay, yeah, we didn't do that in one of my previous examples. Okay, but recall that 1 over 1 minus x is this guy. I mean, we always build from the basics, right? What is going to be the power series form for this guy? This is going to be exactly what we have been doing before, right? For n x to the 2n. So perhaps we can do that together. Okay, so 1 over 1 minus x squared. Wherever you have x, replace it by this quantity. 0 to infinity. I have a negative s squared to the power of n. So now split this guy up. N from 0 to infinity, negative 1 to the n, x to the 2n. Okay, do you see that? N from 0 to infinity, negative 1 to the power of n, and x to the power of 2n. Of course, r is 1. So what happens? The tan inverse of x. Now, okay, so let me not skip step again. So remember, d dx of tan inverse of x was given to be this guy, right? Now, how can I undo this d dx? I have to integrate both sides. If you integrate both sides, so let me just write that in words. Integrate both sides with respect to what? X. If you integrate both sides, it's going to knock off this derivative operator So I'm going to have tan inverse of x integral of 1 over 1 plus x squared dx. But remember that 1 divided by 1 plus x squared, I already have the power series form, which is this guy over here. So just replace that guy, okay? Negative 1 to the power of n x to n dx. Now, but keep in mind that we saw from those properties 3 and 4, this integral can actually operate on this guy inside of it. So it is even okay to bring out this operator. It's okay to bring out my sum, negative 1 to the power of n. Now you're integrating x, not negative 1. So that's why I bring out negative 1. Makes sense. So this guy is n from 1 to infinity, negative 1 to the power of n. Now, if you integrate this guy, what do you get? If you integrate this guy, you get x of 2 n plus 1 over 2n plus 1. Of course, x of 2n plus 1 divided by 2n plus 1 plus a constant of integration. Now, but we cannot really stop here, guys. We cannot stop here. Now, so what are we doing here? We are finding the power series. It's more like we're finding the power series representation for tan inverse of x. But this constant, we need to determine this constant, okay? It has to be some form of values. So now, solve for C. Okay, so now how can I solve for C? Solve for C by plugging in x equals 0, okay? So that means that tan inverse of 0 equals, wherever you have x, just put in 0. Negative 1 to the power of n divided by 2n plus 1. If you put in 0 here, that becomes something like 0 to n plus 1 plus c. In fact, the whole of this guy will go to 0, right? Tan inverse of 0 is 0, so that means that c is 0. Interesting. So I just know that constant is 0, so what does that mean? Thus, the tan inverse of x is the sum as n goes large by 2n plus 1 x into n plus 1. Of course, it's still going to be with the same radius of convergence. Areas of convergence with, let me just say with r equals 1. And the r is just the radius of convergence. Okay, so I know this might seem a lot. When you're watching this video, you can pause it at some point, try to reason along what we have done, or try to reason along what we've, what we've got, and then move on from there. All right. Another example. Evaluate 1 divided by 1 plus x to the 6th dx. Now, we want to evaluate this guy. We're using the idea of the power series. Where do we start from? Solution. 1 over 1 plus x to the 6th. Rewrite this guy. This is 1 over 1 minus, I got to put a negative here. Right? This is, now remember we have to start from the basic thing, right? This guy. From 0 to infinity, negative x to the 6th n. So which I can even rewrite as -1 to the n, s to the 6n. So now I'm free to plug it back into the integral. So you have this guy. Dx equals. Now this sigma notation and this integral can flip. -1 to the power of n integral of x 6n dx. Now when you get a hang of it, it's really going to appeal to you and be easy to work with. -1 to the power of n. If you integrate this guy, what does it give? It gives us 6n plus 1 divided by 6n plus 1. Right? But of course, plus a constant of integration. So over here, we don't have any information to help us determine what the constant is going to be, okay, compared to the other one. All right, so I mean, so far so good. We've gone over 11.9. We started by looking at representation of functions as power series. Started with basic functions, we stepped it up. Then we went on to time by time differentiation and integration. So we see how to treat them. Okay, so we see how to, again, we went on to learn how to shift index. So when you shift index, what really happens? All right, so we saw that as well. And then we saw how we can still use power series to find integrals. Okay, I hope this makes sense, guys. See you in the next section. Bye-bye.